Hello and welcome to our session 8. Let me share my screen. All right, and now hopefully you can see my screen that says session 8, optimization and maximums and minimums. So we are going to be starting with a warm-up question. I'll put it on the screen now in case you want to start it. And then we'll be going through some information about what maximums and minimums are, how to find them, how to do optimization. Then we'll do a couple of questions on that, and then do some exam past paper questions and looking at the mark scheme. And then some exam tips and tricks and questions at the end. If you are joining for the first time, I'm Ashley. Let's get my pen working. There we go. I'm Ashley from Miss IB Maths, working in collaboration with Exam Dojo for these bootcamp sessions. So this is our 8th session. We will have another one on Thursday that is on exam strategy. So not a particular topic, but just some tips and tricks. I am a maths teacher, tutor, and IB examiner. So I'm going to share all of my tips and tricks for the exam and things that I see students do often that, just some tips and things that might help. So that will be on Thursday at the same time at 6 p.m. CEST time. And yeah, if anyone had an exam today, I hope it went really well. And shall we get into it? If you want to answer, then you can put your answers in the chat for anything, or if you have any questions, and I'll try and look and make sure to join them. Hey, nice. Is that for, which one is that one for? I guess I haven't labeled them. But nice, thank you for answering. Let me do it like that. Which way should we go? B, I've made them a bit hard to answer. C, D, E, does that make sense? So starting with a little bit of differentiation. Thank you for the message in the chat. All right, so let's just go ahead and start with those just to get into our optimization and differentiating mode. All right, so the first one, just we can use this notation. If it's y, then it can be y dash or dy by dx, because we're differentiating our function y with respect to the variable x. There's also sometimes this notation that you might see, the dot on top. These are all the same thing. Oop. All right, so for this one, we have 3x squared plus 8x. For that one, just the power rule, 3 in front, take away 1, 2 times 4, 8, take away 1, and that differentiates to 0. All right, B, we can use the product rule because we're multiplying two functions. We could also multiply out. That may be quicker, but let's do product rule just because it's good practice. So what I usually do is I set out my functions u and v. So I say u equals 1 minus 2x and v equals 3 minus x. And then differentiate those. So that will just go 0. That will become minus 2. And this one will become 0, and that will be minus 1, not forgetting those minuses there. So then when we put it all together, we've got to multiply those two, and then add them. So we'll have 1 minus 2x times minus 1. So I'm just going to put a minus 1 in front there. Plus, we have minus 2 times 3 minus x. Let me put that in brackets. 3 minus x, and then just clean that up a little bit. That will be minus 1 plus 2x minus, multiply out there, minus 6, and multiply out there. That'll be a positive 2x. So all in all, 2x plus 2x gives us 4x, minus 1 minus 6 is minus 7. differentiated nice and easily. And C, this is not in the power rule form, so we have to change it first into the power rule form. So we can write that as 3x to the minus 2. And now we can differentiate it. So if we minus 2, multiply that in front, we get minus 6. And then an x, and then we take away 1, so minus 3. That was the one that you were answering. Very nice, well done. And then let's do D. We have a bit of the chain rule. So we are going to multiply with that power of 2 in the front. Then we're going to keep the bracket as is. We're going to take away 1 from the power. See, it's kind of like the power rule. And then we're going to multiply by the derivative of what's inside the bracket. So that's 4x cubed. Minus 3 disappears. We can neaten that one up a bit. Let's multiply the 2 and that term. So that's 8x4. x4. Oh, no, 3. That 3, 8x3, x4 minus 3. There we go. And then let's do E underneath. E, we're using the quotient rule. So again, with E, I like to take my functions u and my function v and write them out like this. It just helps make life a lot clearer. 3x squared, x squared minus 4x. And v was x. This one I'm just going to multiply out to make life a bit easier for me. So when I multiply these two, we'll have 3x4, because we add the powers, minus 3 times 4 is 12, and x squared times an x is an x to the power of 3. Okay, so now we can differentiate that one and differentiate that one. So we have 12x, and we take away 1, so 3. 12 times 3 is 36x, and take away 1 is 2. This one, very nice one. Love it when that happens. All right, so now our rule is a little bit different. We take u dash times v minus u times v dash. So let's do x, 12x cubed minus 36x squared. Minus this time 1 times that whole thing. So we don't need to write that one. X squared minus 4x. Wow, this is looking lengthy. And then we have to divide it, not to forget this step because the quotient rule, by our denominator, which was v or x squared in the rule. We had to square it. And there we go. So, little warm up on our differentiation rules. Okay, so let's get into some of our, we're going to start with max and min this first, and then we'll go to optimization. So just to define a couple of things, we have all sorts of names. We have turning points. So turning points look like this or like this. And it's where the function changes the gradient or the direction. So here we have a gradient of 0. It's just a straight line, gradient of 0. And we're changing from increasing, positive, to negative, decreasing. And here from decreasing to increasing. So when you have that change from positive to negative, we call that a turning point, which makes sense. It's turning point. A turning point is also a stationary point. So these could be called stationary points. But a stationary point could also be like a point of inflection. Ooh. So you can see here there's a gradient of 0, but our function is still increasing after this gradient of 0 there. So that's not a turning point because it's still going to go, it still goes positive to positive. But that's just something, in case they tell you a turning point, then you know that it's going from positive to negative or negative to positive. So to find our maximums and minimum, this would be a maximum up there. This would be a minimum down here. To find these, we have to differentiate f of x, and we get our derivative function. We set it equal to 0 and we solve. And then we get our x coordinates, which are we sometimes called critical points. Critical points. These are the things that we're kind of wanting to find out. Like what value of x is over here. So we need to find those values of x, often called critical points. And then when they want us to find the coordinates of those critical points, we need x and y. So this gets us finding x. And then we just need to find the corresponding y coordinate for that x coordinate using our original function. So if that made no sense at all, let's do an example. All right, so we have our function f of x. Find the coordinates of all stationary points and determine their nature. So when I say nature, well, the question says nature, it means is it a maximum or a minimum? Max or min, that's what we want to know. So first step was to differentiate. So I'm going to take that function. In fact, I might as well write the whole function. 2x cubed minus 3x squared. This is a long one. 36x plus 25. So already I can see this is a cubic function. Cubic, because of that 3, that's the highest power. When I differentiate this, I'm going to get a quadratic. And that quadratic is going to probably have 2 solutions, which means I could have a max and a min from my cubic. So let's see, f dash of x. I know a lot of people say f prime of x and some people say f dash of x. So apologies if you're used to f prime of x. When I say f dash of x, that's what I mean. Just different teachers, different universities and things. It's quite funny how we all have different words. So there we go. There is our f of x function. Now we need to set it equal to 0. So I'm going to just write it again. So we're saying, where is the gradient? Because remember, this is the gradient function. F dash of x is just a fancy way of saying our gradient function. So when the gradient is 0, because that's what a turning point is, what are my x values there? So I'm going to solve this. The first thing I see is that these are all factors of x. So I'm going to, factors of 6. So I'm going to divide every term there by 6 just to make this a little simpler. So I'm going to have x squared minus x minus 6. There we go. So that's way nicer now to deal with. I'm going to factorize, or you could use quadratic formula. So we have x minus, what is that going to be? We need minus 1. So let's do x minus 3, x plus 2. Will that work? Having a bit of an allergy attack. Right, so minus 3 times 2 makes minus 6. Minus 3x plus 2x does make minus x. So I can say that x equals 3 and x equals minus 2. So these are my critical points. Let me highlight them. X equals 3 and x equals minus 2. Now they're really clear for me when I use them in the question. Okay, determine their nature. So are they maximums or minimums? So this is where I have to make a sign table. So I'm going to make 2 points where my critical points are minus 2 and 3. And I need to test values on either side of them. So here I might test, let me put in a different color. I'm going to test minus 3. That's lower. Here I'm going to test 0. That's always a nice number in between minus 2 and 3. And here I'm going to test 4. So see what sign we get, and that will tell me if it's maximum or minimum. So I need to take minus 3 and put it into this equation. So let's see what we get there. F dash of minus 3 is, I'm going to take my easier function. I can do that because it's the same, but it's easier than doing 6 multiplied by everything. Just a bit of an easier function. Okay, so we have minus 3 squared. Let me just draw a line there so everyone knows where I'm taking it from. Minus x, which is minus 3, minus 6. So let's see, what do I get? This becomes positive 9. Remember, minus 3 squared gives us 9. This becomes a positive 3, and this becomes, well, that's just minus 6. So 9 plus 3 is 12 minus 6, which gives us 6. Which is positive. So at minus 3, it's positive. Now let's try 0. F dash of 0. This is nice. We love it when we have 0. 0 squared minus 0 minus 6 just gives us minus 6. All right, so that is a minus, which is making sense. It usually goes positive, negative, positive. Let's try 4 now. I'm running out of space. Let's try it here. A bit messy, sorry. So we have 4 squared minus 4 minus 6, which is 16 minus 4 minus 6, which is 16 minus 10, which is also 6. Interesting. 6 minus 6, 6. So that is positive. All right, so what that tells me, now that I've got that in my sine table, is it's saying my function is increasing here. So you draw an increasing line. Then it's decreasing there. And then it's increasing here again. Positive gradient, negative gradient, positive gradient. So if I'm going up, can you see this makes like a maximum shape? I'm going up and over. And here I'm going down and up again. So at -2, I have a maximum. And at 3, I have a minimum. There it's down, here it's up. So I can say at x equals -2, therefore, is a maximum. X equals 3 is a minimum. Now, AISL, if, well, you have your calculator. So what you can do is you can actually just graph the function. So the original one, so graph f of x, and you'll see the maximum and the minimum points, and you just locate there in the maximum. Let me actually show you because I feel like I'm not making sense. So we want to graph. Let's say I want x squared minus 5x. I'm just making up a random question now. Okay, I want that one. You can clearly see from this graph that I have a minimum value there. And if I want to find the coordinates of that minimum, I don't actually have to differentiate this function to find it. I can just go menu, analyze graph, and I want the minimum. So you have there maximum, minimum. So you can see which one it is. So that's a minimum. I've just got to choose my thing. So there you can see my x coordinate where I have my minimum is 2.5 and my y is -0.25. So you can read it straight off. So that's quite a nice thing of having. And there was also, you could do, let's see, want another one. And just need to remember how, I think you pressed this one and we want a derivative. So that value, oops, oh no. Sorry, just do that again. That button to get our derivative. There's just a bit of a lag. There we go. We wanted dx because that was our variable of f of f1. That was the first function that we had there, f1. You press enter, and it should give you the derivative function. Where did it go? Ooh. Tab. It was called f of x, yeah. Maybe I need to put my variable x. There we go. All right, so there you have, you can also make it graph the derivative function for you. You don't even have to calculate the derivative. You just write d by dx of that function, the f1 function, that was our first one, and you can see it's where it crosses the axis. But either method is fine. And this is how we would do it manually. All right, so let's try another one. So we need to find and classify the stationary points. Now there's another way that you can do it as well. You don't have to use a sign table like we did here on the first derivative. You can also use the second derivative. So in fact, let's do that for this one because that one is going to be a different case. So let me show you how that works for this one, seeing as we're in it. So I could stop at the points that I had. Let's do another color. Let's go in red. So I had those points, x equals 3 and x equals -2. So I could stop at this point before I do my sign table, and I could find my second derivative. So my second derivative would be, going from the first, we have 12x, it's 2 times 6, minus 6, 12x minus 6. That was my second derivative. And then what I can do is I can take these critical points, just going to highlight them again so they're very clear and obvious on the page. I could take these points and I could substitute them in here and see if my answer is positive or negative. So let's take 3, start with 3. So I put that into my function and I get 36 minus 6, which is 30. And that is positive. So if it is positive at that value, positive at x equals 3, that actually means I have a minimum. Positive means a minimum. Therefore, minimum. Let's do it with f dash of -2. That is 12 times -2 minus 6. Just putting that back in my second derivative, that's -24 minus 6, which is -30. So that's a negative answer. Therefore, negative at x equals -2 means that I have a maximum. So you could do all of this instead of the sign table. So let's put that option 1. And option 2. But both methods, you do need the first derivative to find your critical values. So you could use this as well, which can be easier, faster, maybe not sure which most people prefer. So let's try it on this one when we have a little bit of a different situation happening. So let's see what happens. Okay, so I am going to find and classify the stationary point. So first I find my critical points. So I'm going to find the derivative. So that's 4x cubed. Then I need to set it equal to 0 to find my x value. And the only value that works here is 0. If I put 0 in there, I get x equals 0. Right on the other side. X equals 0. Okay, so that's my critical point. So something is happening. So I could do the sign table at 0, or I could go straight to my second derivative, which is 12x squared. And now what I would do in this case is I have that value, x equals 0. So I'm going to put it into my second derivative, 0. So that gives me, well, that gives me 0. And that's neither positive nor negative. And remember what we needed here when we substituted. We needed, if it was positive, we got a minimum. If it was negative, we got a maximum. But here I get 0. So that's not positive or negative. So that means it is, we say, inconclusive test. And that means we have to revert back to first derivative. Revert to f dash of x and do our sign table. So it doesn't always work. Sometimes it does. And if it had worked and not been 0, it would have been nice and quick, actually, without doing the sign table. But it sometimes doesn't work. So your question may ask you to use the second derivative to find it. So you still need to know this. But if you get 0, not positive, not negative, you have to go back. So let's go back to the sign table. Let's pick, should we do -1? Let me do it in different colors so we know that I'm just picking values to test. My test values, -1 and 1. Those are on either side of 0, my critical point. So let's test those values. Let's do f dash of -1 for 4x cubed. So that is minus 1 to the power of 3 is minus 1. So that gives us minus 4. All right, that's negative. Then at 1, f dash of 1, we get 4. I'll write it again, keep the same pattern so people can follow. And that's just 4. So that's positive. All right, so we're going from negative to positive, decreasing to increasing. So that is a minimum. So now we know at x equals 0, f of x has a minimum, which we unfortunately couldn't find from the second derivative test. So we had to go back to the first and do a sign table. All right, so let's start optimization. That will be using maximum and minimum as well, which is why I put them together. So optimization, if you're, is it British English, you use S, American English, you use Z. I use this. I'm not British, but I use the S. Although I think I used to use the Z. I'm South African, so I think we're kind of like a combination of both. But you can use either, none are wrong. We're IB, we're international. So it's the process of finding the value of a variable that makes the quantity a maximum or a minimum. So if you think about, let's say, maximizing the space that you have, if you have a plot of land and you want to build a house on it, you want to maximize the space that you use. So you want to optimize, make it an optimal situation. Businesses often do this. If you think about the tinned cans, they're in that specific, like that height, that radius, all of those things have been thought about really, really well to optimize space, so that you can have your production costs being really low, and getting value for different things. So a lot of these situations will be maximizing profit. Obviously, companies want to get the most profit that they can for the least expenses. Or minimizing the cost of producing something, or minimizing the surface area of a cereal box, or finding the maximum height of a projectile. These are all these kind of questions. So when you hear maximize or minimize, you know that it's an optimization problem. And they follow a very like a template method. So the first thing that you need to do is set up your quantities. So you're usually going to get something like a volume. So imagine you have the volume of a cylinder, pi r squared height. So we have our function. This is the quantity that we're trying to find. Now, if I want to find the derivative of this, at least in the SL level, we don't know how to do with two variables. We can only do one variable. So what we're going to have to do is we're going to have to use a piece of information that they give us. They'll often say like the volume is, I don't know, 100 centimeters cubed. They give us a hint, which is going to help us write the height in terms of the radius, or the radius in terms of the height. So if they've told me my volume is 100, then I can put that in place of 100. So pi r squared height. And then I can make h the subject of that. So I can say h equals 100 over pi r squared. So I've just divided by that pi r squared on this side, and that's given me h on its own. So now what I can do is I can take h and in terms of r and put it back in the formula. So let's have a look at that formula again. I have pi r squared, and then instead of h, I'm going to write my h in terms of r, 100 over pi r squared. And now I have a function that is only in terms of r squared. At the moment, this is not going to help very much, but we're gonna see how that will help. And you can eliminate extra variables. You can simplify. Often the question will say, show that it equals this. Then you differentiate this. So you'll find dv by dr. And then to optimize, you want to find the maximum or minimum. So remember when we found the maximum or the minimum, we had to set it equal to 0. So we'd set it equal to 0, and we'd find the values of x that optimized, that maximized or minimized. So maybe that would be the maximum and that would be the minimum. So if they say we want to minimize the volume, we'd take the minimum x value, just like how we found in the previous way. So that's what optimization is. Using the clues they give you in real life situations, finding the derivative, setting it equal to 0, and then finding the maximums and minimums. So let's see that with an example. All right. Oh, don't have a lot of space. Where am I going to do? Maybe there. Okay. A large allotment bed is designed as a rectangle of length L meters with a semicircle of radius R meters attached to each end. The total area of the bed is 100 pi meters squared. So this is the clue that we're looking for. That's the information that's going to help us. Now, the thing that I would recommend with these is to really draw it out as you get the information. So make sure you fill in what you're given. By the way, a large allotment bed is like one of these garden things. So a rectangular garden shape. So let's do like that. We draw it. There's my rectangle of length L. So I can put that's L. With a semicircle, half circle of radius R attached to each end. So half a circle attached to each end like that. So together they make one full circle with radius R. So my radius to the middle of the circle, I should do it like that rather, so it doesn't look like a line. Let's just do dot, 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 dot. That's a radius, and because that's half of the circle, which means if that's the center of my circles, then that's also a radius, and that's a radius. That's a radius, and that's a radius. So for my rectangle, I already have that the length there of the other side, because I have the length, but what about the width? The width is 2 R's, 2 radiuses. So show that the perimeter is equal to this. Now that looks incredibly confusing. You're like, how do I get that from that? I would recommend that you ignore this for now. If they say show that, it's not helpful anyway, because you can't use this in your calculations. A show that question means you need to go and do your calculations, get to the end, see that it looks like that, and go, oh, there we go. I've showed you it looks like that. But you cannot use this. You can't rearrange this. You can't make it look like it. You must just pretend like they didn't even show it to you. You do your calculations, and then hopefully at the end, it looks like that, or you can rearrange or simplify to make it look like that. But essentially what they want is perimeter. So I'm just going to ignore that whole horrible looking thing and find the perimeter of the shape. So I need to find the perimeter. So how I do perimeter? Well, that's going to be, if I start here, perimeter is all the way going around the edge of the shape. There's an L there and an L there. So I have 2 L's. That's part of my perimeter. Then I also have this over here. So that is of my semicircle, and the circumference or perimeter of a circle is 2 pi r. So I have a full circle here actually, so I can just immediately write 2 pi r. So that is all of my perimeter. I've got everything there. But here it's in terms of L, and here I can just do a quick check. This doesn't have any L in it. This has just R. So I'm going to have to use this little clue that they gave me to get in terms of L. Oh, sorry, in terms of R. So let me just change colors here. The total area of the rectangular bed, they say, is 100 meters. So the area of a rectangle is length times width. So in this situation, I have length, my L, and my width is 2R. So we're just doing the rectangle right now. They've said this area, this rectangle, is 100 pi meters squared. So the width is 2R, and they've said it's equal to 100 pi. So now what I need to do is get this in term just with L as the subject. So to get L as a subject, I'm going to divide by 2r on the side. So I have L is equal to 100 pi over 2r. So now I've got my L. So in this equation, I'm going to take out my L and I'm going to put in this equation. So let's see what that looks like. 2, not L, but 100 pi over 2r. You can see we're getting closer there. Plus 2 pi r. Okay, this is now all in terms of r. It's not really looking like that. So I'm going to simplify a little bit and see what we get. So I can see that there's a 2 here and a 2 here that I'm going to cancel out. So I get 100 pi over r plus 2 pi r. Okay, what am I missing? How can I make it look like that? Oh, I can factor out pi, because you see here they factored out pi. So let's factor out pi. Take out there. We have pi 100 over r plus 2r. And I have an extra 2, no, where an extra 2r there. Have I made a mistake somewhere here? I don't know if anyone can see if I missed something. I factored out 2 over there, 2 pi r. That's strange. I feel like everything that I have is accurate. Length was 2 r's, yes. Over 2r divided by... How strange. It's now one of those moments where you doubt yourself or you doubt the question. Circumference is indeed 2 pi r, and we have 2 of our circles. So okay, I can't see where anything has gone wrong there. So I'm wondering if it's an issue with the question, but I'd love it if anyone else can see something. I'll leave that for now. Yeah. Okay, let's take what the question has for now, just in case, and go with that. So let's say that we found our perimeter in terms of that. So let me just take this to the other side because I want to use underneath there. And so they've said that P equals pi r plus 100 over r. So I'm just going to go with this for now. Even if it's not right, maybe there's a mistake or something, but I'm not sure. So let's just take one. We now need to find the dp by dr, the derivative, and then the stationary point. So let's find the derivative. First, I think I'm going to just multiply that pi back in. So that's pi r plus 100 pi over r. It's just a bit easier to differentiate it like that. Okay, so if I take the derivative of pi r, I'm just left with pi, because pi is just a constant. And then I'm going to have, I need to write this as 100 pi r to the power of 1 minus 1. So I get minus 100 pi r to the power of minus 2. And there we go. I have my derivative. Let me also write it back in its nice form. 100 pi over r squared. And to find the stationary point, I need to set that equal to 0. So write the whole thing again. And solve. Let's put, really running out of space. I think I might take the whole thing and let's just move it over here. There we go. All right, now I can take this over to the other side. So I can have 100 becomes positive. Pi over r squared equals pi. Multiply it by r squared on the other side. Just some rearranging here. Equals pi r squared. I have a pi on each side, so I can divide by a pi. And then I get 100 equals r squared. So r equals positive or negative 10. Not to forget, it can be positive or negative, and you need to show that you know that that gives positive or negative 10, but radius can only be positive. So radius is positive, so r can only be positive 10. All right, so we found the value of the stationary point is that r equals 10. Now we need to classify it. So is it a maximum or a minimum? So our sign table, in fact, it might be easier to do the second derivative here. What do we think? Yeah, let's do the second derivative because we just have to substitute one value of 10. Let's do our second derivative. So our first derivative was up here. I'm just going to highlight it. After the session, by the way, I will go back and just double check the question and my working and make sure I'll correct it in the notes of whatever happened there. So second derivative, we get d2p over dr squared. That's how we write the second derivative in this notation. Is equal to, now the pi is a constant, so that differentiates to 0. Then we have r to the power of minus 2 going up, which when we multiply by minus 2, we get positive to 100 pi r to the minus 3. So r3. So that's 200 pi over r3. In case I did that a little too fast, let me just rewrite this one. That was pi minus 100 pi r to the minus 2. If we write that in a different way, so when we do minus 2 times this negative here, it becomes positive 2 times 100 pi, and then we take away 1 from the derivative, so it gives us negative 3, which I brought back down. So then if in place of that, we now put our r, which is 10, we get, let me just write that now because we can't show it, r equals 10. We're using our second derivative test. We get 200 over r to the power of 3, which is 1,000. Pi, don't forget pi, which is 1/5 pi. Okay. And that is positive, which is what we wanted all along. So if it's positive, that means there is a local minimum. Remember, it's always the opposite of what you might think. Local minimum at r actually. At r equals 10. All right, there we go. And they wanted us to classify the stationary point, which we did at r equals 10. There is a max, there is a min. and find the minimum perimeter. So we would substitute our value of 10 back into our perimeter to find the minimum perimeter. Okay, let's try some exam style questions. How are we doing for time? 15 minutes. Feel free, if you have paper and pen, to grab it and try along with these questions. All right, so here we have a big question, 16 marks, for finding f dash of x. That's a nice one. Then we get some clues, and why I've included this question is because they make it look confusing with saying things like x equals a and x equals b, and a is more than or less than b. I would recommend that you just ignore these. First, just answer the question. So if it has horizontal tangents, you want to find the values of x. That's always going to be the case. And then once you get them, you'll be able to determine which is a and which is b, because one will be more than the other. So let's start with f dash of x. And let me try to answer this neatly on the side, so it's easy to follow. So a. So f dash of x is equal to, well, we're going to have 3 times a third, which is just 1. So that gives me x squared. Then here I have plus 2x and minus 15. This is a Maxman question, by the way, not a optimization question. We'll do one of those next. Great, we found f dash of x. The graph of f has horizontal tangents, lines like that. They're horizontal at these points. So horizontal tangents, the gradient of these is 0. So that means I need to set it equal to 0. It's just another way of asking this question. And solve for x. So let me solve for x. What do we have? Can I factorize? Let's see. I have my factors of 3 and 5 make 15. And 5 minus 3 makes 2. So plus 5 minus 3. Check, we get 15 there, minus 15. And positive 5x minus 3x gives me positive 2x. Great. So x equals minus 5 and x equals 3. But they'd said x equals a and x equals b. So one of these is a and one of these is b. A is less than b. Well, this one's less than that one. So a equals minus 5 and b equals 3. Just a weird way of asking the question, which is just the method that we know. So we found that was b. We found a and b. Sketch the graph of f dash of x. That's a quadratic. So if I want to sketch that, when they say sketch, it just means roughly. If they say graph, it means you have to do it properly, but sketch is a rough thing. Okay, so we have intercepts at minus 5 and at, that's a bit too close, but too rough. At minus 5 and at 3. We have a y-intercept at minus 15, so that could be down here. And now we can draw our curve. Ooh, no. Let me see. Ooh, going through, no. Ooh. Sort of like, oh my word, that's terrible. It's because I've got a writing pad. So it's meant to go through these. Let me just do that. So it looks like it's going through them and through the point. That's not the vertex. This should actually be a little bit more, actually probably more over that side. That's not the vertex at minus 15, just a y-intercept, but that's enough for a rough sketch. Then explain why the graph has a local maximum point at x equals a. So at x equals a was our minus 5. So why is there a maximum point here? And note they're saying why the graph of f. This is the graph of f dash of x. This is the derivative. But they also say hence. Hence means you need to use something that you've calculated or worked out before. So they're not asking for any random reason. They're asking for a reason that you can see from this graph. Very important when they say hence. You need to use the thing before. So why does the graph of f have a local maximum at minus 5? And how can we tell that from this graph? Well, because our graph is going from positive to negative. So if you think about a maximum point is going like this. It's going from positive to negative. And here you can see the graph, if we're looking from this side, it's going down over the x-axis. So here it's positive and here it's negative. It's going positive to negative. And that's why it has a local, a local maximum at x equals a. All right, then find the second derivative. Let's write that over here. F dash dash of b. So our second derivative is 2x plus 2. See, there we have x squared plus 2x minus 15. That gives us 2x plus 2. And they want of b, which was, b was 3. Should be a bracket, which gives us 8. Then use your answer. Again, we have a hence question. Hence, use your answer to part D to show that the graph of f has a local minimum. Remember what we said about the second derivative, that if we get positive or negative, and this is very much positive. Nope, that's not the pen I meant. This one. If this value is positive, that means we have a local minimum. So indeed, there is a minimum. Let me write it in here. That was dii. Local min at x equals 3 because f, the second derivative at that point, is more than 0. So we can use that as a reason. And saying it's more than 0 is another way of just saying it's positive, a fancy way of saying it's positive. Okay, that was an example of how we can answer that kind of question. Let's try an optimization one. Here we have our graph. It was only 1 mark, so really a rough sketch for that was fine. Marks for our differential. Valid approach to solve quadratic. So you could use factorizing, you could use quadratic formula. And see, you get not just a mark for saying that you get 3 and minus 5, but for saying a equals minus 5 and b equals 3. So you had to get those in the right order and you had to state them, not just x equals minus 5 and x equals 3. Nothing too crazy there. All right, how about this lovely looking one? There is a lot of show that questions in these, show that. So again, you can check your answer at the end, but you can't use this in your working. We have 7 minutes. So I'm going to try to do this one in 7 minutes. Okay, we have a solid. It's comprised of a cylinder. So let me just start by writing volume of a cylinder, or we're using surface area, but let's do. So cylinder, let's get a, in fact, let's go to our formula booklets and whoop, just go and see what we have so we get used to seeing them. Which this is interval, which should be the same, but anyway, they might just be in different places. So, sorry, that's my dog if you can hear him. Volume of a cylinder, they're all in different places. So this is another thing, is to know your formula booklet well. And while we're on this topic, some people forget that there's prior learning. So in prior learning, you get a whole bunch of formulas. So if you're thinking, I'm sure that this formula was in my formula booklet, but I can't find it in geometry or trigonometry, it's probably in prior learning, and this has confused a lot of my students. Okay, so volume of a cylinder is there, but I think more of the ones that we want are in trigonometry, which is this. So here we go. We have volume of a sphere, surface area of a sphere. Let's take those. And I thought we had surface area of a cylinder, but I think there it's not. Oops, I don't want to put that there. Let's put it here. Okay, and we were having the volume of a cylinder was pi r squared height, and the surface area of a cylinder, it's just helpful to have these already before you even start. Of a cylinder, we want if we flatten out the surface area, it's like a rectangle with little circles on each side. So the surface area of each circle is 2 pi r squared, because there's 2 circles. And then this area of the cylinder, this is the same as the circumference of the circle. So if we want this, then we're taking circumference, which is 2 pi r. So plus 2 pi r times the height of the cylinder, pi r squared height. So that's surface area. And then for volume of a sphere, we have 4 over 3 pi r cubed, and surface area 4 pi r squared. So we've got those to start with. Now let's have a look at the question. It's comprised of a cylinder and 2 hemispheres, which is half spheres. The cylinder has a height of h, okay, that's normal, and the radius is x. So instead of r, we're going to be using x. The hemispheres fit exactly onto either end of the cylinder. So that's just saying we don't need to worry about any empty space. The volume of the cylinder is 41 centimeters cubed. So this is our clue that they always start by giving us in optimization problems. That's going to help us put one variable in terms of the other. Let me write in blue. So the volume is 41 centimeters cubed. Show that the total surface area of the solid is given by this formula. So we want the total surface area. First, let's get our volume, use that volume clue to get our height in terms of radius. So I'm going to write that down here. Volume equals pi r squared height. And they said volume was 41 centimeters. So 41 equals pi. We had x squared for radius. There was x and h. Now let's make h the subject of the equation. So we divide by pi x squared on the other side. There we go. Now we have h in terms of the radius, which is x. Now let's put that all together to get surface area. If I want the surface area of this shape, I'm going to need the surface of one full sphere, because we have half and half. So let's write that as SA for surface area. Of one full sphere, that was 4 pi r squared. 4 pi r squared. And then we want the surface area of this rectangular part. So we don't want these circles, actually, because the circles are covered here. They're not part of the surface area. So we just want the rectangular part, which was highlighted in a different color now. For the surface area of that part was just this, without the circles. So we want plus 2 pi RH. Have I lost you, or are you still following? 2 pi RH. Maybe if I draw in a bit of a shape, let's see. So this 4 pi r squared, that was for these parts, the ends, that surface area. And this was for this part of the cylinder when you roll it out. So we don't use those parts. That's this part here. If that's rolled out, that's just a rectangle. Okay, and now let's put it in terms of our variables, which was x for r, and for h, remember we'd written h in terms of x. So let's put that all together. 4 pi, don't need to put brackets. 4 pi x squared plus 2 pi x, and instead of h, 41 over pi x squared. Okay, that's all in terms of x and no h. So Let's simplify that a bit. 4 pi x squared. Then we have a pi and a pi cancelling there. An x and an x squared cancelling there. 2 times 41 is 82 over, all that's left there is a little x. And now let's go back and see, does it look like what they said? Show that. Yeah, 82 over x. There we have our 82 over x. And 4 pi x squared, 4 pi x squared. Lovely. So we've shown that the surface area of the solid is that. So we wouldn't get a mark for that, but we'd get a mark for all of this showing it. The total surface area of the solid has a local maximum or local minimum at x equals a. So this value of x, which we're now going to call a. So when we find it, just don't forget to call it a. Find an expression for ds by dx. So as usual, and I shouldn't call this surface area, they've just called it s. Now I need to find ds by dx. What's the derivative? So here, 4 pi x squared, well, I multiply by 2, so that gives me 8 pi x. And here I have minus 82x. Woo. Messy. Over x squared for that derivative. So I found ds by dx. That's my expression. Hence, find the exact value of a. So what that means is I need to find my x. So I'm going to set this equal to 0. And instead of x, I'm going to write a because now they've called it a. Doesn't really change anything. Now I've got to solve. So let's put 8 pi a equals 82 over a squared. Oh, my pen's going funny here. Multiply by a squared on both sides, so I get a cubed. On the side, divide by 8 pi on this side, so I get 82 over 8 pi. And finally, I'm going to cube root my a. So if I cube root my a, I get on this side 82 over 8 pi. There we go. What a beautiful answer. Put that in a box so it's clear. That is my value of a. Isn't that lovely? Looks like quite a scary value. So, and that's also a note that if your answer doesn't look pretty, it doesn't mean it's wrong. Right, then find an expression for the second derivative, which I think I'm going to leave it there because we are out of time. But you would just take this value, just like we did in the previous questions, and find the second derivative. And then you could substitute this value into your second derivative. And if it's positive, you have a local minimum. And if it's negative, you have a local maximum. So same sort of method. So here you see the questions. They say, find an expression for the second derivative. Use it to justify that it's a minimum. So you would get that it would come out as a positive value and it would be a minimum. And then once you have that, you take that value and substitute it into your surface area formula, which you have over here to get your minimum surface area. And that's just substitution. So hopefully that all made sense. There's a lot of algebra as well going on in there and simplification. If anything didn't make sense, please let me know. Be happy to answer any questions. In the mark scheme, I think there was nothing really different or interesting, just a lot of algebraic solving. Don't forget to round your answer at the end to 3 significant figures. We'll talk more about these kind of rules and things in the strategy session on Thursday. Yeah, nothing crazy. And I have some more questions here with answers and things. Also a PDF that I have now. Some people asked me for it, but I hadn't put it together yet. I've now put all of the session notes and exam questions into a folder. So if you've sent me a message, I'm going to send you the link this evening. And if you would also like to get that link to all of the session notes and more exam past paper questions, you can message me here at Miss IB Maths. My arrows need some work. on Instagram, Miss IB Maths, and I can just give me your email address and I will share the folder with you. Or if you have any questions at all, I'd be happy to help. So yeah, always define your variables. When the question says show that, every step must be really, really clear. If you skip too many steps in between, then they assume you've just adapted the show that to look like it. They can see right through it. And make sure you reject invalid solutions like negative lengths or times, things that don't make sense in real life. Remember to reject those solutions. As usual, notes are over here in this on Exam Dojo at Learn. I will put a homework assignment for session 8 on the exam prep bootcamp M26 class. So all the class codes on an info page. And done. A little bit late, but any questions? Anything you want to know? Anything that didn't make sense? Anything that you want to see coming up? Let me know. You are so welcome. Very much appreciate the feedback. Thank you. Very, very welcome. Any other questions? Anything at all? I'll wait a couple of seconds just in case anyone's typing. So there will be sessions, like I said, on Thursday for exam strategy. So not a specific topic, just talking through tips and tricks and anything I recommend, like timings, how to pace yourself, how to leave answers, how to answer different kinds of questions. And then on Saturday and Sunday, there will be another 4 sessions. So look out for that and watch the space. Okay. Well done for joining, and I wish you all the best with your exams that are coming up in either this week or next week. I hope the studying is going well, and you got this. You're almost at the end, so well done. Okay, where were we? Sharing. Goodbye, and have a lovely, lovely evening.